Now let's take a look at several processes and boundary work associated with them. First, we are going to discuss about constant pressure processes. Here we have a piston cylinder device that is going under a constant pressure process, and if we try to plot it on a PV diagram, we will have a diagram like this: a straight horizontal line from state 1 to state 2, and we know that the area under the curve is WB, boundary work. So we can write that the boundary work is equal to starting pressure, which maintains at the same level throughout the process, into final volume minus starting volume. If we are writing it in terms of specific volumes, we can write WB is equal to mass of the gas inside the piston cylinder device into pressure into specific volume change. Now let's take a look at constant volume processes. Here, when the volume doesn't change, the PV diagram is a vertical line from state 1 to state 2. So what is the boundary work for such a process? You can write WB, boundary work, is equal to the integration of P dV, and the dV is equal to 0, so WB is equal to 0. So constant volume processes doesn't produce any boundary work simply because the boundary does not change. Isothermal processes are another important type of processes that we are going to discuss frequently. The idea is temperature does not change. So here I have a piston cylinder device with air inside. So it is an ideal gas inside the piston and cylinder device, and I am compressing the system while keeping the pressure at a constant level. Since it is air, we can use ideal gas equation. We can write PV is equal to mRT naught, T naught being the constant temperature that we maintain the air at. Mass, universal gas constant, and temperature does not change throughout the process, so we can write mRT naught is equal to C. So PV is also equal to C. PV changes throughout the process, but their multiplication, PV, maintains at constant level C. So I can write P1 V1 is equal to C and P2 V2 is equal to C. Also I can write this equation: P is equal to C divided by V. So in my boundary work equation, I am substituting P using C over V, and I can integrate it C ln V2 over V1. To get the value of C, I can substitute P1 V1 in this equation. Also I can substitute P2 V2 into this equation. It is important to remember that this equation only applies to an ideal gas because we assumed it's an ideal gas to start this derivation. Isothermal expansion is very similar. It's only the reverse of this process. So the same equation applies for isothermal expansion process. Polytropic processes are another type of processes that you are going to see in future. At the moment, you have to remember a polytropic process is defined as a process where we keep PV to the power n is equal to constant. You will see the practical importance of this later. So with a bit of mathematical magic, we can derive this equation. It is important to remember this is also only applicable for ideal gases.